And it's my pleasure to welcome Dr. Jennifer Carter. So Dr. Carter began her research in exoplanet science while earning her doctorate in physics from the State University of New York at Albany. And she's now assistant professor at Susquehanna University. And her current work focuses on the use of Bayesian data analysis methods to model and characterize reflected and thermal light of exoplanets, especially across their surfaces. So, Dr. Carter, I'll turn it over to you. And thanks again so much for coming out today.
Thank you for having me. All right, everybody. Today we're going to be looking specifically at the photometric emissions of exoplanets. As mentioned, part of my work is dealing with Bayesian data analysis. To do that properly, we need to have a forward model for the exoplanet light curves that I use as part of my research. With that in mind, let's just very briefly make sure we're all on the same page when I use the term light curve. We're concerned with the amount of light versus time coming from a star system where we have our host star and our exoplanet orbiting the host star. I think we're all familiar with the main change in the amount of light, which occurs when the planet passes in front of our host star. You see that loss of light. It's called a transit. And it depends on the size of the exoplanet. In this talk, I'll use RP for its radius, and the host star will have a radius of RS. Larger exoplanets block more light. But we also know that there's a lot more detail to be found in these exoplanet light curves. You see an increase in light along here until we reach nearly a maximum, and a second loss of light. Well, this maximum is occurring because we're getting light from the exoplanet. Just like the moon, exoplanets go through phases if they're aligned correctly or along our line of sight. My talk today is going to be talking about this light from the exoplanet itself, those planetary photometric emissions. We lose those during the secondary transit. Very broadly speaking, these come in two main forms. It's the addition of the reflected light, which depends on the geometric albedo, AG. I tell my students this is how shiny the planet is. Shinier planets, of course, reflect more light. It also depends on the size of the planet. Larger planets receiving the same amount of light and our equal shininess will reflect more light. And it also depends on little r, the star-planet separation. That is because the amount of light received by the exoplanet decreases with star-planet separation. We have to take that into account. Less light received, less light reflected. This is going to be an ongoing theme in this talk. The other main piece has to do with thermal radiation. This is, again, a very broad look. We can get into a great deal of detail when it comes to thermal radiation and reflected light at this point. But broadly speaking, the amount of light lost during the secondary eclipse is the black body flux from the day side of the exoplanet. And we've normalized this to the black body flux from the host star. And it's, again, dependent on the size of the exoplanet to the host star. I want to get into a lot more detail about reflected light now. But first, I want to talk about why I'm so concerned about the way we treat reflected light and the incident stellar radiation that actually causes this reflected light. This comes from two papers written a number of years ago. In 2013, Lillebox was studying Kepler-91b, and the authors of this paper pointed out that 70% of this hot Jupiter's atmosphere was at least partially illuminated, and that we ought to be taking this extra illumination into account. Normally, we tend to assume that the illumination of an exoplanet is closer to 50%. Later on, colleagues of mine, Plasek et al. In 2015 was studying Kepler-91 again, proposing that there might be a Trojan candidate. In other words, Kepler-91c would have been an exoplanet with the same orbital period and star-planet separation as Kepler-91b, but in its orbit, it would have been 60 degrees ahead or behind. But they ended up dismissing this as a false positive because using Bayesian data analysis and their forward models at the time, the temperature estimates for Kepler-91c and b were not physically correct. Things like the night side temperature being hotter than the day side temperature. Now, this could be because our model is not correct. It's not difficult to mistake thermal light for reflected light and vice versa. Separating the two is a challenge, and it's certainly a challenge if we do not accurately model them. So that brought me to my main research regarding reflected light. Let's talk about the assumptions we often make when characterizing reflected light of exoplanets. The first main assumption we make is regarding the nature of the incident radiation on our exoplanet. We often assume that they come in plane parallel rays. This works very well if the planet is far from its host star. In that case, it's perfectly reasonable to assume our incident rays are just nice and parallel, and our planet is half illuminated in this fully illuminated zone and half unilluminated. So we get two illumination zones in this case. We, of course, know that this is not physically correct. If that were the case, then on Earth, the sun would set instantly and rise instantly at what this line is called is the terminator. We don't experience that. We see the sun rise and set all the time. People who are watching the sun rise or set are in the Earth's penumbral zone. So in my research, I want to take into account as precisely as possible the finite angular size of our host star, where we treat the host star and our planet here as spheres. And in this case, we end up with three main illumination zones. The fully illuminated zone here, within that zone, the entire apparent disk of the host star would be visible. And it's defined by these two inner tangent lines, tangent to both the surface of the planet and the star. Illumination ends in the unilluminated zone here. That's defined by these two outer tangents. Everything in between is the penumbral zone. Now, this particular figure is a bit exaggerated to illustrate this geometry. Typically, our penumbral zones are quite a bit smaller, but they can become quite large. Let's compare and contrast these two models looking at Kepler-91b. And rather than using the analytical approach I hope to be able to use, let's look at it numerically. Shown here are two models for Kepler-91b. On the left-hand side, we have a case in which the semi-major axis A has been artificially set to be larger at 10 astronomical units. At this point, the plane parallel ray case works just fine. And our numerical models suggest that during quarter phase, half the planet is, a quarter of the planet rather, is reflecting light towards our observer, and everything else is not reflecting light because it's not receiving light or it's not visible. And during new phase, we see no reflected light. Using numerical models for Kepler-91b's true star-planet separation, or semi-major axis, I should say, of 0.072 astronomical units, this is what we get. We see that much more of the planet is now reflecting light. It doesn't appear very uniform. There's this gradient that we don't see in the plane parallel ray case. And most importantly, during the new phase of the exoplanet, which occurs during that primary transit, we actually receive light from reflected light of the penumbral zone, because that penumbral zone always extends to the far side of the exoplanet when you properly take into account this finite angular size. Further, we can produce numerical illumination maps. Here again, we see a case in which the plane parallel case holds when the planet is set far from the host star. I want to point out these dashed lines. These dashed lines would mark the terminator of our exoplanet, that halfway point. And in this case, we have no illumination on the planetary far side. This is not the case when we actually do the proper accounting of the finite angular size of the host star. Here, we start to see a relative intensity of about 0.2 or 0.1 in near the terminator of our exoplanet. Finally, Let's look at, instead of a surface map, something we can actually measure, luminosity versus time, or our phase curve, our phase function for just reflected light. And here in blue, we have a case where the plane parallel case holds. And of course, in orange, we have the case where it does not hold. And you see that we always have more light reflected by the exoplanet when, of course, more of it is illuminated. And this is greatest, the difference between these two is greatest during that new phase. Let's call this delta. The value of delta changes based on the star-planet separation and the size of the exoplanet. Let's see a surface map to illustrate when this finite angular size is most important, when we really need to pay attention to it. Shown here is the value of delta as a percent versus scaled semi-major axis, where we've scaled it to the size of the host star, and the scaled planetary radius. And we see that it's at a maximum for small star-planet separations and also for smaller exoplanets. But it's clear here that the star-planet separation matters a bit more. And there's a reason for that. The star-planet separation is actually what really sets the size of our penumbral zone and governs how far it extends into the far side of the exoplanet. Let's see why that's the case. Here, I want to just introduce two variables, eta1 and eta2, where eta, pull out my model, is measured from the polar axis to some other point. Eta1 tells us the limits on our fully illuminated zone here. Try to align it. Eta2 tells us where the unilluminated zone would begin. And we see that they depend on the size of the planet, the size of the host star, and the star-planet separation measured center to center is little r. We also see something else that's really important here. The unilluminated zone, in this case, always starts on the far side of the exoplanet. We also see that as star-planet separation increases, both of these polar angles will decrease, heading towards zero. In other words, we reach our plane parallel rate case, and half the planet is lit, half of it is unlit. Let's actually see the relative size, the fractional surface area of some exoplanets within each of these zones, the fully illuminated and penumbral zones especially. Shown here is a table with the top 5 here are potentially habitable exoplanets. And I want to draw your attention to the fractional area, sigma full, within the fully illuminated zone, and the fractional area within the penumbral zone. The addition of the two is the fractional area lit. For these 5 exoplanets, I've ranked them mostly based on the size of the penumbral zone. And we see that the largest one for TRAPPIST-1d is 2.5%. These 5 exoplanets are from the NASA Exoplanet Archives, that confirmed data set where we actually have measures of the radius of the exoplanet and some idea of the star-planet separation. We see that the largest penumbral zone for K2183b, and this is as of, I got this data back in May, so it's a little old, but it shouldn't change too much. Anyway, the penumbral zone for this planet is a whopping 71.6% of its fractional surface area, for a total area that's at least partially lit of 84.8% of its surface area. Here at number 5, we have the hot Jupiter, Kepler-91b, and we see that it is nearly 70% fractionally partially lit. I also included Mercury and Earth for reference. If we look over at these equations, we see how the size of each zone is related to the size of the star, the planet, and the star-planet separation. Because the penumbral zone only depends on the size of the star and the star-planet separation, which I always find really interesting, It's always going to be the nearest planet that has the largest penumbral zone in any star system. So Mercury has the largest penumbral zone within the solar system at 1.2% of its surface area. And on Earth, 0.5% of its surface area is within the penumbral zone at any given time. This is just the fractional area of the planet within each zone. What part of the planet is within a zone can change. Although with how close most of these planets must be to their host star for the finite angular size to truly matter, I expect many to be tidally locked. Now that we've gotten a sense on the potential sizes of these zones, let's take a look at the confirmed exoplanet population at time of creation of these graphs. These are looking at confirmed exoplanets with astronomical semi-major axis of 1 astronomical unit or less. First plot is looking at number of planets versus the percent of the planet within the penumbral zone. We see that over 500 of them have a penumbral zone that takes up more than 10% of their surface area. So too, when we look at percent illuminated, more than 500 of them have 55% or more of their surface area at least partially illuminated. Finally, we have this scatter plot, and I like this because it gives us a bit of a sense of size, location of these exoplanets. This is semi-major axis versus stellar radius. The color corresponds to percent within the penumbral zone. Here, it's very clear that the majority have a penumbral zone of 10% or less, but we have quite a number with greater penumbral zones. And right here, we have one of the largest at, I believe that is the 70-ish percent one we saw earlier for K2813b. We see here that quite a number of exoplanets have significantly sized penumbral zones. Now I want to talk about how we might actually calculate the luminosity due to reflected light within the fully illuminated zone and penumbral zone, because that is what we would observe from a transit light curve. It ends up being fractional luminosity, but first we get luminosity. To do that, I want to define a few variables just so we know what the variables are when we get to later equations. The phase angle in this case is going to be epsilon. That's this angle between the substellar point S and the subplanetary point E, where I have set the positive y-axis to run from the center of the exoplanet towards the host star. A lot of other researchers actually set that to the positive x-axis. For my purposes with later integrations, it's a lot easier if we take advantage of the symmetry about positive y. So I've set that as the positive y-axis. The subplanetary point, just so we remember, is the line that lies on the surface of the exoplanet along the line that connects you, the observer, to the center of the exoplanet along this line of sight. We've already seen eta, which measures the polar angle of some point P on our exoplanet. Phi is going to be the azimuthal angle. And there's two other angles that are important when dealing with reflected light. The first is the angle of foreshortening, gamma. This is the angle from some point P to the subplanetary point. This tells us about the projection of light coming from point P along our line of sight. The other important angle has to do with our incident radiation, gamma prime. This is the angle between point P and the substellar point. For the plane parallel ray case, when we have large star-planet separations, this corresponds to the angle of incidence. I'm going to show you later on with some other graphs that that's not the case when you have to consider the finite angular size of the host star. And the fact that sometimes these planets are within 2 or 3 stellar radii of their host star. So even then, the size of the host star is very important when we consider the projection of the light coming from the host star toward our point P. because that gets us an important thing, the incident radiation, which is what I want to talk about at this point. In order to get luminosity, first we have to understand the reflected intensity distribution at some point P, some little bit of our exoplanet here. To do that, we need two pieces of information. Var rho here is our reflection function. For the purposes of today's talk, we're going to keep it very simple. This is just going to be a constant. It's going to be the single scattering albedo for our exoplanet. You could use whatever other function you want, so long as you know the incident radiation at point P. How do we calculate that? Well, we do a little bit of trigonometry, geometry, and integration. Shown here is our host star and our exoplanet. The incident light at point P here depends on the intensity of the host star as a function of theta prime. For the purposes of this talk, we're going to again keep it relatively simple and assume linear limb darkening, where U is our limb darkening coefficient. So we take this light coming from some point Q on our host star. We need to project it towards point P using this dot product here. Next, we need to consider the fact that the surface area of the host star visible at point P depends on this dot product here and this thing here, which I'm going to talk about later. Finally, instead of dealing with the star-planet separation, we need to account for the fact that each point Q is a bit closer to each point P over here using rho prime. That's the distance between point Q and point P. And we square it because then intensity falls off as 1 over r squared. Now, our strategy to integrate over the surface area of the host star is to integrate over omega and theta. So omega and theta. This is actually going to be one of the sources of our problems in analyzing the incident stellar radiation. In particular, because of this bit here, we only want to integrate over the part of the host star visible at point P. And there are two main zones to consider, the fully illuminated zone and the partially illuminated zone, the penumbral zone. Let's start with the fully illuminated zone. Oh, before I forget, in this case, alpha is our angle of incidence rather than gamma prime. And it's easy to show that these two are about equal for large star planet separations. So let's look at the fully illuminated zone. We don't actually see the half hemisphere of the host star in this case. We only see the full apparent disk, which forms a spherical cap between these two tangent lines between point P and the star. Within the fully illuminated zone, this horizon at P, which is just a plane focused at point P and tangent to it, does not intersect the surface of the host star. So our strategy then is we want to integrate over omega. That's easy for a spherical cap. You just go 0 to pi and multiply by 2. Now, instead of integrating over theta, we're going to integrate over rho prime because we have a line of symmetry here. Nice and straightforward. I'm not going to go through this integration. Instead, I want to show you results. The incident radiation received at a point P within the fully illuminated zone for linear limb darkening is given here in terms of mu, which is cosine of gamma prime. And it's written in terms of these Legendre polynomials of mu, which is great. This is actually, the integration gives you an exact result that turns out to be a generating function for the Legendre polynomials. However, when you go on to calculate luminosity, it turns out that integrating this intensity distribution ends up being non-analytical. But we have it in terms of Legendre polynomials. So instead, we're going to expand out to whatever precision we wish. I'm going to discuss later on how far out we're actually allowed to expand, given our assumption that these two objects, the star and the planet, are spheres. For now, I want to look at the illumination within the penumbral zone. Within this zone, some part of the host star is cut off by the horizon at P. And I can do this nice and easy with a camera. I love this. So here we're within the fully illuminated zone. Within the penumbral zone, some part gets cut off, right, by the horizon along the bottom of my camera here. Pretend this is a star. To account for that, we can use some angle lambda, call that the geometric depth of the eclipse. It determines how much of the star is visible at point P. Now, previously, these ideas had been applied to eclipsing binary stars to study the reflection effect by Koppel back in the 1950s. In his work, he only considered one penumbral zone. This worked well enough because he was actually looking at the larger of the two stars, not the smaller. Here, we're looking at exoplanets, which are always smaller than their host star. Otherwise, we're not looking at exoplanets. If you try to use his results on cases such as this, you end up with negative luminosity and imaginary incident radiation, which is, of course, not physically correct. This is due to neglecting some important sign changes. Let's take a look at a solution to this problem. There's not actually one penumbral zone. There are two. The first one, nearer the host star, penumbral zone 1, sees more than half of the stellar disk. The far one, penumbral zone 2, sees less than half of the stellar disk. The dividing line between the two of them is here. It's tangent to the surface of the exoplanet and points towards the center of the host star. I want to point something out here. Penumbral zone 2 always starts on the near side of the exoplanet and extends to the far side. If we look carefully at our model here, you can see that's the case. It's only ever a little tiny bit, but it does start on the near side. If I recall, the sign of the polar angle there is RP over the star-planet separation. Let's talk about how we might approach calculating the incident radiation within these two zones. My goal is to do this analytically as far as possible, because that tends to play nicer with the data analysis methods I use to analyze exoplanet-like curves. I'd like to avoid numerical solutions. So for now, let's take this as far as we can analytically. The first step within penumbral zone 1 is to look at the apparent disk of the host star. So this is a projection of what you would see within penumbral zone 1. The white part is visible to our observer. This part is not. It's not actually really easy to integrate over just this part here. Instead, it's easier to integrate over the whole spherical cap and then subtract this spherical segment along the bottom. To do that, we're going to have to find our omega limits in terms of theta. These depend on the theta, some location on the host star, and lambda. In other words, how deep is that eclipse? And you can do some trigonometry to show this is the case, properly taking into account signs. Finally, we integrate over theta, starting at the geometric depth of the eclipse and ending somewhere down here. For penumbral zone 2, there are fewer steps. We only have a spherical segment that's visible. Again, we take advantage of some symmetry and we integrate omega from 0 to some maximum and multiply by 2. Here is our limit on omega 2 in terms of theta with this nice right triangle to guide us, and our integration over theta. So here is that integral we would have to perform within the penumbral zones. we have an idea of the limits that would go here. Unfortunately, the integration within those spherical segments is non-analytical. We can get the spherical cap just fine, but within the segments, we run into some problems. So what's left to us to continue with an analytical analysis, or semi-analytical at this point? We can do an expansion. We expand about things that are approximately small, like RS, the size of our host star, divided by rho, which is the distance between some point P and the center of the exoplanet, as well as cosine alpha, which can be written in similar terms. How far do we take this expansion? Since we are approximating these as spheres, we really can only go out to fourth order. This was something that Kopel pointed out in his previous work. Going beyond that, we need to start treating these as ellipsoids, which I haven't begun to study yet. This work is ongoing. We have an idea of our approach, but the analysis for these integrals is continuing. Once we get those integrals to actually get the incident stellar radiation, we can then integrate to get luminosity. I've already done this for the fully illuminated zone. Let's take a look at some previous results and current results just within that zone. First, how do we approach it? Of course, we integrate our intensity projected along our line of sight and integrate over the exoplanet. We can only integrate zone by zone. So we want our limits of integration to reflect two things: which zone we're in and the phase of our exoplanet, because it's the phase angle that governs how much of each zone is visible. To do this, I'm going to define an integral operator to make things a bit easier, because otherwise we end up with page-long integrals. Instead, we use this operator. We insert the luminosity within whatever zone we care about, and this bit governs our limits of integration. Chi talks about each zone, right? Where does it end and start here? And then we have phi naught and phi f. This tells us where to start our integration. And there's two main cases to consider. If the zone is completely visible, we would start here and end here. The phi's just are governed by those locations. If instead the zone is only partially visible, we would start here and end at the limb, which is a function of phase angle epsilon. The integrals we are writing down are of this form. And in order to perform this correctly, we integrate over each zone, add up each zone to get the total luminosity. There are 7 distinct cases we actually have to consider. So we have to perform this integration 7 times. Well, some of them we just get 0, so we don't integrate in that case. And we take this thing out to fourth order. More on that in a moment. So there's quite a number of integrals to perform. Now here are our 7 cases, and I'm not going to go into too much detail. I just want to point out that the reason there are 7 instead of something like 8 or 9 is because the size of these zones, well, they're not all the same size. Things like the fully illuminated zone, well, that's always going to be a bit smaller than our unilluminated zone. So it disappears in the timing is just different, so that it works out to 7 cases rather than say 8. Now, let's get to the exciting part and look at results for the fully illuminated zone. I mentioned previously this work had been done for eclipsing binary stars. If you naively try to apply this to exoplanets, you get things like negative luminosity and discontinuities when we look at fractional flux versus time. This has been fixed by my previous work. This is the fractional flux for the fully illuminated zone only, where we've taken it out to fourth order in our Legendre polynomials, because that's as far as we're allowed to, assuming these are both spheres. The purple line is comparing this to an exoplanet of the same size if we treat it as a Lambertian sphere and use the plane parallel ray approximation. We see that there's always less light from the fully illuminated zone. This makes sense. The fully illuminated zone always takes up less than half of the surface area of the exoplanet, right? We don't expect it to emit more light. We always expect it to emit less. Down here is the difference between the purple curve and this multicolored curve. And we see it's at a maximum somewhere near quarter phase. It's not exactly at quarter phase. Again, this is only due to the fully illuminated zone. So we're not seeing this being at a maximum difference at new phase. I judge this delta phi as a very rough estimate of the total flux that might come from the penumbral zone from Kepler-91b, at least during quarter phase, less so near new phase. I don't think that applies as well during new phase. All right. What about the penumbral zones? Again, if we naively take the approach used for stars, we get negative luminosity, and this is just the real part of the graph. This doesn't include the imaginary results that popped up. How do we fix it? Well, we really need to determine those incident, rather the reflection intensity distributions. If we get lucky, fingers crossed, it will turn out that these come in the form of polynomials in mu being cosine of gamma. I've already done those integrals in the process of analyzing the fully illuminated zone, in which case a lot of our work is already done for us. All we have to do is figure out what these coefficients are, and we'll get our luminosity within these penumbral zones, and this will be fully analyzed for the finite angular size of host stars taken into account. What about temperature? I mentioned that reflected light and thermal radiation can be entangled with each other. One of the things I noticed when I was finishing up my dissertation was that if I wanted, I could take these 4 zones and assume that each zone was at its own temperature based possibly on the amount of light received in each zone. Well, then if we treated them as black bodies, the intensity distribution is really simple. It's just a constant based on the temperature and the size of the zone. I had done all those integrals already. So I decided, why not go a little further? We don't have to use this geometry. We can consider things like eyeball worlds, something that might look like this. And we have a lot of different options here. We can assume that the temperature at the substellar point is the greatest and least over here, that it's decreasing monotonically because less light is received as we move away from the host star, or we can let it vary. In addition, we also really want to be able to move this hottest zone to some other location than the substellar point. So I decided to experiment and see what I would get if I continued using this model. Shown here is a look at Kepler-91b, making a few important assumptions. Here we're assuming a monotonic decrease in temperature from hottest to coolest, because otherwise there's no way to really make a fair comparison between a 2-zone case where we're just looking at something like what Placek et al. Was looking at, a day and a night side, and an n-zone case where we have 4, 6, 8, or 10 zones. In plot A, I'm using results from Placek et al. Where the hottest temperature is the day side temperature and the coolest is the night side, just to make a comparison. You'll notice that the difference isn't very great because the difference between these 2 temperatures is not very great. But we notice some important patterns. As we increase the number of zones, the fractional difference increases, but there are diminishing returns. The difference between our 4 and 6 zone model is a lot greater than the 8 and 10 zone. This implies to me that one of the important questions we can ask is how many zones do we even need to describe the temperature gradient of an exoplanet, assuming that it's monotonically decreasing. I also decide, well, let's look at what happens when we increase the temperature gradient and we get something that looks like this. A much sharper change in the comparison occurs during things near quarter phase. And we see the maximum magnitude of this difference occurs during the new phase of our exoplanet, which makes sense. That's when we're receiving a lot more light than we would expect from thermal radiation, because a lot of this night side is hotter than would be expected in a 2-zone model. Well, we can extend this, and instead of looking as a function of time and number of zones, let's look at 2 important points in the orbit. Here we have the planet when it's at its new phase during the primary transit, and here we have it when it is at its full phase, which would occur during the secondary transit. Let's look at those 2 points and produce some surface plots. This is the absolute value of that fractional difference between a 2-zone case and n equals 4, 6, 8, and 10. We plot this fractional difference with this color plot here. Minimum temperature is this value, maximum temperature is this value. Again, assuming a monotonic decrease. Otherwise, there's no way to really produce these plots effectively. We see a couple of things. This one, again, is the primary transit, secondary transit, excuse me. This one occurs during the primary transit, much greater, nearing 200%. This occurs because I was basing this off of Kepler's response curve. And for small temperatures, that approaches 0 for its detection. We start going outside of its detection limit. So we end up with very large percent differences because the denominator here is nearing 0. We see that same pattern. The difference increases with number of zones. There's diminishing returns, and it also increases with temperature gradient. The largest difference occurs for something like a 5,000 Kelvin substellar point temperature and a 2,000 Kelvin minimum temperature. So we start to ask ourselves, can we use Bayesian data analysis to determine how many zones are needed through model testing? And in addition, what are the temperatures of those zones? We can either assume monotonically decreasing, this reduces computation time, or we can allow the temperatures of these zones to vary. That increases computation time though. So if you have a reason to believe that it's monotonically decreases, it's a good idea to start with that test first. Let's take a moment to conclude. We have a few choices with these thermal radiations. We can either assume it's based on incident stellar radiation and just have these 4 zones, or we can extend it to something like this, and we can possibly combine the 2 and see what we get and estimate things like number of zones and their temperatures. I said this part. Moving to the future, I want to model for that hotspot offset. And there's a very important reason why. While testing on archival Kepler data on the hot Jupiter K412b, I noticed that the most favored model in my tests, where I held the mass of the planet constant as determined by radial velocity data, and included things like boosted variations and ellipsoidal variations, which I'm not going to discuss today, and just thermal light. We neglected reflected light in this case because I haven't finished that analysis yet. We get the following thermal light shown in magenta. As a reminder, 0.5 corresponds to the primary transit in this plot. And we see that there's a dip in light, implying that this substellar point temperature is cooler than this temperature. That's what we find. I think that this might be because it's actually trying to account for a hotspot offset, but it's doing it in this odd way because this temperature and this temperature would be equal. So we're getting some odd temperature distributions. In addition, let's return to reflected light and wrap up here. Many planets do have large penumbral zones. We saw this for K2183b in particular. If we look at latitude, the penumbral zone starts on the near side of the exoplanet at 79 degrees latitude and ends something like 46 degrees latitude on the far side. This also means that the incident radiation within these penumbral zones, that's what governs how much light is received at the poles of our exoplanet, assuming that it has zero obliquity. So the axis of rotation is not tilted to the orbital plane. It's been shown using global climating models that polar ice coverage can have an effect on global mean temperatures. To my knowledge, no climate models actually take into account this type of radiation here and here. We treat everything as if it's within the fully illuminated zone. And even within potentially habitable exoplanets, we can have something like 1%, something like roughly here, that would be within the penumbral zone. These models are further used as inputs into other programs, and the error just carries on. So we ought to take this into account. Finally, we need to account properly for the nature of the incident stellar radiation to account for reflected light and therefore thermal radiation of our exoplanets. I want to conclude now by thanking everybody for joining me. I want to acknowledge that this work was supported with the research publication grant in engineering, medicine, science from the AAUW. I want to thank Michael Way for helping arrange this talk and Joe for introducing me. I also want to thank all of my current research students for the last couple of summers: Michelle Arrigo, John Morris, Jocelyn McMahon, and Amanda McLaughlin. They've done a lot of work helping me analyze some of this, get this into ExoNest, and start testing it on exoplanet data. Thank you all for coming. What questions can I answer? How are we running questions?
Oh, thank you so much, Dr. Carter. That was really, really interesting talk. Anyone is welcome to raise their hand if they have any questions, or you can also post them in chat. I think, actually, I'll have Mike go first. Go ahead, Mike.
Thanks so much, Jen. That was really great talk. I really appreciate you going through all those details for us. My obvious question, which I always ask you, I think, is when are you going to give us lookup tables for our GCM so that we can take these things into account, especially for people doing, close in hot Jupiters, which we've discussed in the past is really critical for them.
So you remember that thermal radiation stuff I was talking about? I thought I was going to be able to get a paper out for that right away since the math was easier. So once that's done, I'm going to be returning to this reflected light stuff in earnest. So given that I teach at a small liberal arts college, it depends if I manage to put together a collaboration strongly. With more help, I could get this out a lot faster, but during the school year, I don't have a lot of time to do this research. So I'm extremely interested in grouping together with other researchers to work through this and get those lookup tables together, whether or not they're numerically produced or analytically produced.
Right, because I remember reading your thesis. I felt like 70% were integrals.
How long was my appendix? Like 30 pages of integrals?
Yeah, something
double spaced. That's enormous.
It was pretty impressive.
I have Mathematica files that are multiple megs in size.
Yes,
but anyway, other questions?
Probably, do you want to go ahead?
Yes, really great talk. I think I was telling Joe, I was like, there've been people who've done this in kind of hacky ways, including me. And this is a really actually full treatment, which is awesome. One of the things that you mentioned is how many zones you might need for some of these cases. And you showed that kind of day side, night side, near side, far side difference. That's definitely going to be, like you've alluded to, related to the planet star separation distance. So is it, because I think about hot Rockies sometimes, and I think, well, as you get closer, I might want more zones. So is there a way you can be like at this particular separation, maybe, or you're not tightly locked, maybe whatever else, we don't need too many zones, but for a really close in thing like 55 Cancri or something, you might need a bunch more?
You of course need a physical reason if you want to make these assumptions ahead of time. Now, something that was mentioned at the beginning of this is that I typically use Bayesian data analysis. So my answer often is, well, you just have to run the numbers and see which one has the larger evidence. And once we've done that for a variety of planets, we start to develop a physical reason to do so in the future. We've observed, for example, that rocky planets that are this close to this size star, I usually refer to scaled star planet separation because that seems to matter the most, especially for this reflected light stuff. Then you use that information for your next analysis. That's how we learn, right? I think for very close in exoplanets, you might need more zones rather than less. Is looking at this geometry and some of the numerical models that colleague of mine, Kevin, put together. Kevin Knuth is way at the beginning. Yeah, this guy. Visually, just visually, you see much more of a gradient, even just with that incident light and than the reflected light. So if we assume, as we should, that the thermal radiation is coming at least in part due to heating from the host star, which is a little mapped here in reflected light, then it seems reasonable that to account for this weird gradient, we might need more zones than we do in something like this case, where it's very clearly like half of the planet really just receives all the light and half does not. But this doesn't account for other things like winds and transport of that energy, which is a bit outside of what I study. I'm mostly concerned with the nature of the incoming energy, not how it gets redistributed.
Yeah, I think top of the atmosphere fluxes, even if you have that, that would be awesome. Because yeah, then it starts to get really complicated in the atmospheres and surfaces and everything.
I've always told people, it's like I get the first result and then hand it off to the climate modelers. Other questions?
Make Michael do the work. Thanks, Jennifer.
No problem.
Any other questions? I have one. This may be a naive question. This isn't this isn't my expertise, but I just had no idea that this had such a large effect. So this is really, really cool to learn about. But this slide is actually perfect for what I wanted to ask. Is can you talk about anything about the errors that you can get in your observations if you're not taking this into account? Because I'm just looking at like this new phase diagram. Like, would somebody looking at a close-in exoplanet that doesn't take into account these effects, could they be making wrong assumptions about the size of the atmosphere or even the radius of the planet?
That is something that I did think about when putting my thesis together. It's like we're getting extra light that we are not properly accounting for. This is going to reduce the depth of the eclipse and therefore our estimated size of the radius of the planet. As far as numbers like percent error, I'm not sure, but maybe with this numerical model already put together, we could get a rough estimate, at least for Kepler-91b. I might have to email Kevin Knuth.
Yeah, I mean, that would just be really, really interesting to get any of that. And also, like, what does that mean for the spectral analysis? Like, if you're getting parts of the night side mixed in with parts of the, I
I've
don't know.
also
There's a
thought
lot
about
there.
refracted light, right? If you're not accounting for light coming in over here, how are you going to account for how it's refracted by the atmosphere?
Right.
You can't.
Yeah, there's a lot. There's a lot
I
here. This is
suspect
really,
it
really
would
cool.
produce an error. How much is hard to say because since it doesn't receive as much light, it's not going to reflect as much. So I imagine the error would be small. I also imagine it being larger for larger exoplanets that are close to their host star, just based on the size of the zone increasing in that case.
Mhm.
Yeah.
Yeah, well, going back to what Prabal was saying, like 55 Cancri might be a good example of one that could be primed for having a lot of errors on this.
Yeah. Ball keeps trying to rotate away.
All right. Well, Prabal, go ahead.
Yeah, and just to chip in, I mean, just extending this because you have this kind of formalism written up. Thinking about when you have escape and then you start to have like Roche lobe overflow and something like helium, that would be interesting to see what the effects of this are in terms of, you know, how that changes kind of the thermodynamics of whatever gas you're looking at escaping. So yeah, I think there's a lot in different kind of spectral regions that would be really interesting.
Very neat. Thank you for sharing that. Yeah, there's all sorts of ideas that I'm interested in learning more about, like how this can be applied elsewhere.
It sounds like everyone on this call needs to collaborate with you going forward.
Give them my email.
All right. If there's no other questions, let me just wait just a second to see if there's anyone else. Doesn't
See
look like
anything in
it.
chat. I have you guys on my other screen.
Oh, perfect. Well, again, thank you so much, Dr. Carter, for coming out and talking to us today. It's really, really interesting talk, and I hope the end of your semester goes well with grading.
Yes, thank you.
All right, thanks everyone. We'll see you. Our last talk for this semester is next week, and then we're off for the holidays. So we'll see everyone then. Take care.
Thanks, Jen. Take care.
Bye. Thank you.
Bye, everyone.
Bye-bye.